Hello, welcome to our next set of notes for mathematics reasoning. We're on our last section for statistics, section 6D. We're going to be talking about inference. Up to this point, we've been mostly looking at our sample data and measuring it, doing things like finding the mean, mean, mode, measuring the variation. But honestly, the biggest part of statistics is actually taking the sample data we collect and trying to learn things about the population. So here, kind of a little picture here. This is a really good representation. Big part of statistics is, we want to learn about some huge population, but we can't talk to everybody because there's too many people. That just takes too much time, too much money. We're trying to find something out, like maybe the population mean, the average for the entire population. So what we do is we take a random sample, just a small sample from that group, and we measure the sample, the mean for that sample. So we measure the average. So instead of trying to average everybody, because we can't, get that data, just too expensive, take too much time to, sample everybody, we take a small sample, find the average for that small sample, and then we have to look at that and say, okay, based on this small sample, what can we conclude about the entire population? We're not sampling everybody, so we don't usually expect our sample mean to be the exact same as our population mean, though in statistics class we would talk about how you can expect it to be close. It's reasonable to say that it's going to be kind of close to the population's average. And this is how it works for anything, not just the average. We could think maybe like the percentage of a population. If I'm trying to do a study, maybe find out what percentage of people went to college, I would take a sample and see what percentage of that sample went to college. So our big thing in statistics is taking a small sample and inferring some conclusions about the entire population from that sample. Now, here's a little example of how this kind of works and some of the reasoning we have to do with this. So say you take a normal coin, and when you toss it, 50% of the time you should get heads, and the other 50% of the time you should get tails. That's pretty typical for a normal coin. Suppose you toss your coin 100 times, and you get 52 heads and 48 tails. Now, would this lead you to believe it's a trick coin? And I think the answer is pretty clearly no. We don't say, okay, just because it's not exactly 50-50 that it's a trick coin. There's some randomness, some chance. Just because we only flipped it 100 times, we didn't flip it, 1,000 or even 1,000,000. We're not going to maybe get exactly 50-50%. We're going to get an example, an answer. So if you flipped 100 coins, but you got 10 heads and 90 tails, would that lead you to believe the coin is unfair? And that would probably be yes, because at this point, that's a pretty drastic difference from what we were expecting. We were expecting like 50 and 50, and we got 10 and 90. So a big part of doing statistical inference is you look at your sample and you look and see if it's unusual, if it's not what you expect. Because if it's very unexpected, if it's unusual, it actually would probably mean that the data you're looking at is different than from what you thought. If you think the mean of a population is 5 feet 7 inches, and you take your sample and you get like 6.5 feet. That's way higher than 5 feet 7 inches. So then you start thinking, well, maybe my assumption that the mean was only 5 to 7 inches was wrong. Maybe this group is taller than that. So that's what we do. We take a sample and we look for things that are unusual. So we call this, when a measurement or observation, we call it statistically significant when it's unlikely to occur by chance. So when you get a value, you get a result that's just not what you expect. So it's unlikely to occur by chance. We call it statistically significant. So as far as we're concerned, something that's unusual, something that doesn't match up with your expectations, that's significant. So the actual results don't match your expected results. So here's a couple examples. We're just going to determine, are these statistically significant? So say you draw 100 cards from a deck of 52 cards. So you shuffle, draw a card, shuffle, draw a card. You do it 100 times. Probably make a computer do it because we don't have to do that 100 times. But you do this 100 times, drawing from this deck, and you get Jack of Spades 30 times. Well, Jack of Spades is just one card out of this deck of 52 cards. So what we'd normally expect is we'd probably say about every 52 draws, you're going to get that once. So you do 100 draws, we'd expect 2 Jack of Spades. That's what our expectations would be, because we only expect it to come up 1 out of 52 cards, because there's 52 cards in there and only one of them is Jack of Spades. So if I draw about 100 times, I expect about 2. If I got like 3 or maybe 1, I probably wouldn't freak out that much. Here we're getting it 30 times. This is very much not equal to our actual result of 30 draws. And we would say, yes, this is significant. Now for me to look at that, so there must be more than one Jack of Spades in that deck. It might be like a Pinnacle deck, because there's like Pinnacle card decks that have extra face cards like Jacks of Spades. So maybe it's a Pinnacle deck, or maybe it's a trick deck, but you'd say, yes, this is significant. And the reason it's significant is not because we got lots of Jacks or little Jacks, it's because we got different from what we expected. And lots was why we got different. That's the thing. It's not about having a lot. It's about having something different than what you expect. So yes, this is significant. We were only expecting 2. We got like 30. Say you flip a coin 40 times and 24 flips come up heads. So first off, what we would expect? Well, again, coin flips, it's 50-50 usually. So out of these 40 times, we'd expect about 20 flips, right? We're looking for 20 flips to be heads, because there's 40 flips, and about half those, 80%, should be flips, should be heads. We got 24, and that's close enough. It's not super different. It's not exactly the same, but in 2024, they're fairly close. We'd say, hey, that's not that far off what we were expecting. And so because they're too close, they're not that different, we'd say, no, this is not significant. I'm not going to think this is a trick coin just because I got 24 heads instead of 20 heads. That's just going to say, hey, that's just random variation. That's just the randomness of chance. Not a big deal. It's a little bit different. If we had done this and gotten 5 heads and the other 35 or tails, then we start to go, okay, maybe there's something up with this coin. Like that's the kind of weird, and this is significant. But this one's not, because they're just too close. You roll a 6-sided die 120 times, and you roll a 5 10 times. So 6-sided die means there's 6 sides, 1 through 6. If I roll it 120 times, well, I would expect about 1/6 of that. So if I divide that by 6, would give me about the number of times I expect each number. So here I'd expect the 5 about 10 times. So my expectation for this, but 20 times. 6 goes into 120 20 times. So I expect about 20 10s or 5s. So I'd expect 20 of them. We only got 5. That's not that far off, but it's far enough. We might start wondering, hey, this is kind of significant, because I was expecting 20 of these. I only got 5. Now, you could double check this. If you're going, well, that seems still kind of close to me, I want to be more sure, you could roll more times, and that's one way you could sample. If you take a bigger sample, if you think it might be significant but you're not sure. But yeah, this time I'd say, oh, I said 10 times, not 5 times. I keep doing the wrong number. 5, so 10 5s. Yeah, that's what we got. And I'd say, okay, that's about half what we were expecting. We were probably expecting a few more than that. There's still a chance that maybe this isn't, anything special. It's just randomness. But I'd say it's probably not close enough for me. So maybe I'd say yes, significant. When it comes to the test and stuff, I probably ask you about if something's significant. I will try to make sure it's very obvious that it's either significant or not. If it's fairly close, it's not significant. When it's super far away, when it's super off, you're expecting, something 30, a couple times you got 30 of it, or if you're expecting a whole bunch of times, you only got a couple. That's what I'll do on the test to make it really clear on the test. But this is the idea. If your expectations are matched by what you actually get, you say, hey, it's not that big a deal. It really probably doesn't mean anything. What we expect to be true is probably true. But then when you do a survey and you say, hey, this is very different than what we expect, then that tells us things. And this is how people do real surveys. This is how they, analyze their survey results. Is they go out and they do a survey and say maybe they're looking at what percentage of this state is getting college degrees, and they take a random sample, and they kind of have an expectation. They know maybe the national average or the published average from the last census or something like that. And they take that expected value and then they look at the current value and say, okay, is it significantly different from that? Is it very different? And then they'll say, oh yes, it's very different. Yes, it's significant. And they'll tell them that the value is probably different than what it used to be. Or if it's not very different, if it's kind of close to what it was before, they'll say it probably hasn't changed. It wasn't a significant difference. It wasn't that much different. So that significance is important for statisticians. We look at what we were expecting to get and what we actually get, and we try and see how close those are. The further apart they are, the more we say, okay, this data is really meaning something to us. Now, you can kind of see from that last part where it was kind of hard to say exactly how much that meant. It's kind of necessary to quantify this. We were just kind of saying this in general sense, and that's mostly what I'm going to do on the test, is going to do this in a general sense so that it's really clear. But on the homework and stuff in the book, we talk about how you can kind of quantify or measure this definition of significance by using some probability a little bit. So we quantify statistical significance based on the probability of the observation. So what is the likeliness of the observation occurring by chance without any change or without any difference? We say if the probability of observed difference is at most 1 in 20. So if it's like less than 5%, so 5% or less, we say the difference is statistically significant at the 5% level. We would usually call that moderate significance. So stuff below 5%, we're going to say, hey, that's significant, but it's only moderately significant because 5%, that's like a 1 in 20 chance. It could still happen sometimes by accident. 19 out of 20 times it's not by going to happen. So it's still pretty significant, but that's moderate significance. If instead the probability is less than 1 in 100, so the probability is at most or less than 1 in 100 or 1%, versus the 1 in 25%. So now here this is like 0.9% or 0.7%. Then we say it's highly significant. So it's statistically significant at the 1% level. This is high significance. So if I go out and we do my study and we get our result and we say, okay, wow, that result is so far from the expected result that we're really sure that this is, way different. This is so far a probability of getting this result based on, what we thought things were is only like 0.5%. And we say, hey, this is highly significant. This means that we probably have to reject our old understanding and, change what we think about this. Now, it is also possible that your probability is actually high, more than 1 in 20, so more than 5%. So this would be like a 7% or 10% or 20%. Anything higher than that, we're going to say that's not significant because that could happen. If it's like 10% chance, well, at 1 out of every 10 surveys is going to hit that, and we might just spend that one. So, go and do a college study and find out that, we thought it was 75%, and we get we get 72%. That's not that far from 75. They're really close together, and we say, hey, there's like a 10% chance that we got 72% just from the sample we picked, even though the real value for the entire population is 75%. Because again, when you go and do your study, you just pick a small sample of people. Your result won't usually match up exactly with the population result. The entire population, there's an actual average for the whole population, or percentage, how many of them go to college, and we said it was 75%. Our sample, again, we just picked a sample. It's not everybody. It's just a part of the group. And we got 72% from that sample, which is fairly close to 75%. We know that's going to be true. They're usually going to be close. But it's so close to us for us that we would kind of go, it doesn't mean much. Now, if we thought it was 75% and we got a sample of like 60%, that's way further away from 75%, that would lead us to believe that maybe our understanding of 75% is wrong. Maybe over time that's changed. Maybe the old survey was wrong. So we'd say, okay, no, there's a difference. So that's the idea. So again, the higher the probability, the less we say it's significant. That's more likely to be, it's close to what we thought it was going to be. The further it is away from what we thought it would be, the more different it is, the lower the chances get, and the more significant it gets. So high significance, it's all about being below that 1% level. So here's a couple examples. So say a medical research center begins testing a new cancer treatment, and they find that groups of patients treated are living significantly longer. Yay for that! The cancer treatment's working, people are living longer than those that don't receive treatment. If the research can show the probability of this happening by chance is 0.6%. So there's a probability when you do a new drug, test a new drug, there's a chance that you just picked a sample group that was just going to live longer. They were going to fight the drug off, the cancer off, whether or not they got your drug. Drug didn't do anything. There's a chance. That's always something that's possible. We try to avoid that. We don't want to be giving medicine out there that's not really doing anything. There's no point in it. So they have to look at that and say, okay, what's the likelihood based on the size of the sample they pick and how bad the cancer is, so what are the chances this group just tends to be the longer living group? That could happen. Well, they figured out the chances 0.6%. Well, that's really low, right? That's less than 1%. So is it significant? Well, yes, this is significant. This cancer drug treatment is probably actually doing something, because we can check and we can see that there's less than a 1% chance that these people are living longer just by chance. The drug is probably doing it. So because it's less than the probability is 0.6%, we can say because that 0.6% is less than our 1% cutoff for high significance, this tells us that yes, it's high significance. So we can say that we think that the drug, the cancer treatment, is actually helping people live longer. High significance. This is mean the researchers definitely state the treatment is a success. And so we'd say, yes, the treatment is a success. Now, in real life, they have really stringent testing, precautions where they say, okay, we got to do all this research before we can really say if a drug is good or bad. And so they might have to do several studies, so from different people, different groups, but that's basically at the end of the day what they do, though. After they do enough of these trial runs and have enough people try out their drug and look at the results, they look and say, okay, can we say now, do we get enough evidence to show that the drug is actually helping these people and helping them live longer? And if they get enough evidence, then they can put that out there and say, hey, we can show that our drug is significantly helping these people with they're living longer, they're fighting off the cancer better, and then they go sell the treatment. That's the idea. Let's try one. Same medical research center is testing another drug and finds that patients treated with the drug experience an effect of weight gain. They're looking at side effects now, because that's a big thing. When you develop a new drug, you have to worry about what side effects it has. So this one looks like it's making people gain weight. If the researchers find the weight gain has a 10% chance of occurring amongst this group of patients, without any drug influence. So again, this is the idea that we picked a random sample of people. There's a possibility this group, they might just gain weight. We have to think about what's the likelihood that happens. And they figured out, they did some probabilities and calculating, and they found out there's a 10% chance this group just gained weight, versus other groups, the control groups that didn't receive the drug. Well, that's really high, right? 10% is a pretty high chance. So 10% chance, because it's so high, we're going to say it probably doesn't have anything to do with our drug. We're going to say it could be just the fact that the people just randomly were the group that gained weight. This might be a reason why they might go back and do their drug study with a bigger group, because the bigger group, the less chances that group is going to just gain weight randomly. They might, should be gaining more weight than anybody else, than the control group. So we'd say, though, in this case, because 10% is so large, 10% is above that 5% cutoff, it's in this last group, it's not significant. So we'd say it's not significant. We don't think that that's really important. It's probably not the cause of their weight gain. There's 1 in 10 chance they just gained weight just because that's the group we picked. They probably should, they don't need to worry really too much, because that's greater than 5%. But they probably should redecide their study or do a bigger study so that they can eliminate that as a possibility. So don't need to worry. But that's actually something when people design like research studies and try and test new drugs, they try and make sure their sample group is big enough so that they can tell if things are by chance or if it's not. And so because they didn't use a big enough sample, or they didn't design the research study very well in this situation, they ended up with this weight gain having a 10% chance. If they had designed it better, they probably could have lowered that chance, and then if it would have happened, they would have known. So it's probably a bad study, but the idea is we're looking at the percentage and we're looking at how high it is. We'll see this actually come up in the second project you're going to do, the M&M's project. So the probability of something occurring is important. Again, if the probability is low, that's when you say, hey, this is telling us something. Now we need to incorporate that information. If the probability is too high, if it's greater, the higher the number, the greater the probability. If it's too high, then it's not really telling us anything. It's not inclusive. So that's something we'll really see showing up here later, and especially in the project data. Okay, next part of this is dealing with margin of error and confidence intervals. So like we mentioned, we take a sample from a population and we calculate what's called a statistic. So the statistic is going to be like the mean or the percentage. It's the value we calculate from that sample group. So when you take a sample of, high school kids and you find their average weight, that statistic, that average weight would be the statistic. We don't expect those to match exactly with the parameter. So parameter is the value for the entire population. And so it's just fancy names, statistics. So like that mean, the average weight for the entire, student body, that would be the parameter. The statistic would be the average weight for just the sample we looked at. Those are the differences. Parameter is the true value for the entire group. Statistic is the value for the small portion we studied. And a lot of times what we're doing is we're trying to use the statistic and kind of guess things about the parameter. So based on the size of the sample, we calculate what's called a margin of error. So the bigger your sample, the less room for error you have. The smaller your sample, the bigger your margin of error will be. So basically we say we don't expect the statistic and the parameter to match exactly. I go out there and I measure the weights at the school and I get 180 pounds is the average for my sample statistic. But the true average is probably going to be somewhere close to that, but it's probably not going to be exactly 180, because how likely is it we got an exact number from the sample we picked? It might be a little bit higher. It might be 190, 192, something like that. It might be a little bit lower. It might actually be like 175, 176. So it's probably close to 180, the sample value we got, but we don't know exactly what it is. So what we do is we create some wiggle room around our value. We take our sample 180 that we got, statistic, and we say, okay, add a little bit of wiggle room on both sides. Say, okay, it could be a little bit higher, it could be a little bit lower. And then we say we are confident that the actual value, the average for the entire population, is going to be within this interval. So that's called the confidence interval. So a big part in using a sample to understand the whole entire group is creating a confidence interval, which you do by using the margin of error. So the margin of error, again, is based on the size of the sample. So based on the size of the sample, we'll create a margin of error. And then using that margin of error, we'll create a confidence interval. And it's the range of values where you can be fairly confident you are including the actual value. That's what the definition of a confidence interval is. So to create your confidence interval, we take our value from our study, from our sample, and then we add or subtract the margin of error to the value, and it gives us our confidence interval. So I'm actually going to add this formula to the formula sheet. I haven't had it on there before, but I want to make sure it's on there now. This is something you really need to know how to do. We'll see it show up in the project. You're going to see it in the homework. You'll see it probably on the test. So to find this confidence interval, we calculate the statistic. Again, statistic is just the value for your study, usually a percentage or a mean or average. And then you subtract the margin of error to get the low end, and you add the margin of error to get the high end. So you basically make this interval where the value is going to be within this interval. For example, study shows that 36% of students change their major with a margin of error of 4%. So based on the size of their sample, they say, okay, we have to give 4% wiggle room. That's our margin of error. So to get the confidence interval, they took that 36% and they subtracted 4%. And so on the low end, it would be 32%. And they added 4% to 36% to put it on the high end to be 40%. Now, that doesn't mean that we think the answer is 32% or 40%, but what it means is we think the actual percentage of students that change their major is somewhere in the range between 32 and 40. It could be 32, it could be 33, it could be 38, it could be 39, it could be 40, but somewhere in there we think it is. And now we're not completely positive. We can't be 100% because 100% is too hard to do with just a small sample. You have to measure the entire population to be 100% sure. But we can be fairly sure. In fact, most of the time we'll probably be like 95% sure, which is pretty sure. If you're 95% sure about something, you're very sure about it, and you're not really worried about not having it. The size of this confidence interval we'll see on the next page is actually based on how sure you want to be. The more sure you want to be, the bigger you have to make your confidence interval. So it's kind of not helpful sometimes. If your confidence interval gets too big, that might not be helpful. So we like to try and keep that limited a little bit. Okay. So we're going to build some confidence intervals for these following studies. So it is shown that on average, college students attend 8 movies per year with a margin of 2 movies. So again, they went and they sampled some college students. They didn't talk to every single college student because that takes too much time, too much money. But they got from a sample, they found that they had an average of 8 movies per year, and their margin of error was 2 movies. So this is their statistic, because it's what they got from their sample, and the margin of error was based on their sample size. So 2 movie margin of error. So then to find a confidence interval, we're going to take 8 minus 2, and we're going to do 8 plus 2. So we're going to say, okay, at the low end, they might get 6 movies per year. At the high end, they might get 10 movies a year. But we are pretty confident our confidence interval is that there's going to be somewhere between 6 to 10 movies. So the average number of movies the college student watches is in the range somewhere between 6 to 10. I think I mentioned this last section. All my numbers in these kind of surveys and stuff are made up. So if you're sitting there going, wow, I watched like way less than, way more than that, don't worry about it. I just made these numbers up, so they don't really mean anything. But that's the idea. Confidence interval, we're fairly confident the actual number of movies the college student watches in a year is somewhere in that range. This is why if you go look up things like what's the average height of a man in the U.S. or what's the average weight of a high school student in the U.S., if you look up stuff like that, they don't just give you one number. They give you a range of values. It's because how they did the study, well, they went and they took a sample and they said add the margin of error so that they get some wiggle room, and so they know that the real value is somewhere within that range, somewhere between blah and blah. That's how it works. That's how they do it. So you can't tell you exactly the exact one number because no one can measure that whole group. You know, the entire population of the U.S. is so big, and it would take so much time and money that just never would happen. But they can give you a range. You say from our sample, we can say it's going to be between here and here. Let's try another one. So it's shown that 70% of mothers rely on family members to babysit their infants with a margin of error of 5%. So 70% of mothers is going to be our statistic. Margin of error is 5%. Again, I'm just going to take the 70%, subtract 5, so I get 65% on the low end. I'm going to do 70 plus 5, I'm going to 75% on the high end. And that's how this works. Now we have a confidence interval. Even though our study said 70%, we don't really think we probably got exactly right on the money because we only took a sample of these mothers. We didn't talk to every single mother because that's too many. But we can be pretty sure because of our margin of error, we know that the actual value is probably going to be in their range between 65 to 75. So somewhere in that number, somewhere in that range, is the actual percentage of mothers that rely on, need family members to do their babysitting. So that's value is going to be somewhere in that range. Last one, showing that 48% of new businesses fail within the first 5 years with a margin of error of 3%. So there's extra numbers here. You gotta be careful. Here that says first 5 years. That's just time frame, right? So it's 48%. That's your statistic. Margin of error 3%. Now this one says, would it be valid to claim 50% of new businesses fail in the first 5 years? So if someone said that, and you did this study, because a lot of times we do studies like this to check people's claims, would you believe this person? Would you say, oh yeah, that makes sense, or would you say, no, you're full of baloney? Well, 50%, if I look at the 48% and say, okay, 48%, I could subtract 3 and say on the low end it could be 45%, but I could also do 48 plus 3 to see on the high end it could be up to 51%. I say, hey, 50% is definitely within this range. So between there, you could fit in 50% because that's between 45 and 51%. So because it does fit in this, confidence interval, because we made this confidence interval and checked and say, hey, it fits in there, we'd say, yeah, that's a valid claim. It makes sense. If I was the person double checking this person's numbers and I did the study and say, hey, I got 48%, 3% is my margin of error. So it can be anywhere between 35 to 51. I'd say, hey, I have no reason to disagree with this person. Their claim makes sense. And this is actually what we're going to do. The last part of this is we're going to do testing claims. And this is one way to test claims is you build the confidence interval and then you just check. Is their value they claimed, is it within your confidence interval? And if it is, you let it fly. You say, that's good, it works. There's nothing wrong with their claim. But if they're outside of your confidence interval, if it doesn't fit, that's when you start to suspect them. And you say, hey, I don't think your numbers, your values, your claims are making sense. And that's what statisticians do. That's one of their jobs, is to sit there and test claims. When a company makes a product and they say, hey, the weight of our product is this many ounces, the government actually goes and they sample, periodically they go and they find a company and they sample so many of their boxes and they look at the average weight. And if it's not close to what they said, if it's not, within a reasonable amount, then they'll actually find them and say, hey, you're over advertising, because you're saying this is what it is, but it's actually something different. So that's one of the ways they check those That's by doing this confidence interval thing. They take a sample, they build the confidence interval, and then check and see if the claimed value is within the confidence interval. Okay. Now, the most common confidence interval, and the one we're going to use, is called the 95% confidence interval. So far, I've been just giving you the margin of error, but usually people have to find that themselves. So when we construct the confidence intervals, first have to find how confident we need to be. So how certain do we want to be that we have our value within the confidence interval? The more certain you want to be, the bigger your confidence interval needs to be. And so that can kind of get kind of ridiculous. So most people stop at 95%. Yeah, you could do 97, 99. There is, people that do like maybe a 99% confidence interval because there's a certain situation where they have to just be more confident. They don't want to miss. But most people in general do 95% confidence intervals. That's the most common type of confidence interval. And there's a nice way to calculate the 95% confidence interval margin of error. And that's the formula right here. It's on the formula sheet, but the formula, if you want to find the margin of error for a 95% confidence interval, then you do 1 over the square root of n. Remember, n is the sample size. We've used this before, but n is the sample size. You need to know that when you get to the test. The n is the sample size. And this is for a 95% confidence interval. On the test, if I ask you to find the margin of error for a 95% confidence interval, I can't tell you how many times people are trying to use 95 as part of the problem. The 95% is just a label. It's nothing to do with the percentages. It's just a label of how confident we are. That's all it is. So it's not going to affect like the confidence interval. It's not going to affect the margin of error. It's just telling us that this is the kind of confidence interval we want. We're not doing 90%. We're not doing 99%. We're doing a 95% confidence interval. It's the type of confidence interval. All it really tells us is if you have that kind of interval, use this margin of error calculation. So, for example, I've got a poll of 1,250 single mothers. We found out 64% of them have more than one child. We want to find the margin of error, and we want to construct a 95% confidence interval. So first off, before I can build the confidence interval, I need to find the margin of error. So I'm going to use this margin of error formula. And again, because they said we're doing a 95%, that's why I'm using this margin of error. That's really all this 95% is telling me. Hey, 95%, well, that's the margin of error. So I'm going to do 1 over square root of n. And n is the sample size. In this case, they polled 1,250 women, single mothers. So n is 1,250. So I'm actually doing 1 over square root of 1,250. I'm just going to type this in my calculator. Works the same on the TI-30. I'm just using my TI-84 because it's nicely bright and lit. So I'm going to type 1. I'm going to divide it by. So that's just my division button. And then I'm going to use my second and hit square root. So my square root button. So it's got the little square root symbol above it. That's why I did second to make it do the blue option. And then just type in 1250. So I'm doing 1 divided by square root of 1250. And I get 0.028. This becomes 0.028. Notice that this is in decimal. We're dealing with percents, so I want to make sure I turn this to a percent. That's pretty typical for these You have a sample number, and you'll want to find a percent for your margin of error. So I'm going to take this and turn it into percent. So I'm going to do the decimal 2 spots. So this will become 2.8%. So be ready on the test as well. When you find your margin of error, be ready to turn it to a percent. Okay, now that we have the percent, now we can build a confidence interval by taking 64% and subtracting 2.8 and doing 64% plus 2.8. So this one gives us 66.8, so that's the high side. This one, that's what, 61.2, so 61.2%. And so we are now 95% confident. That's how confident we're in. This is a 95% confidence interval. We're 95% confident that the actual percentage of the single mothers that have more than one child is in this range. Again, all my numbers are made up, so don't think too much about them. But this is the range. So somewhere between 61 and 66%. We got 64% from our study, but based on our sample size and wanting to be 95% sure, we'll say, okay, the actual value is probably somewhere between 61 and 66%. It's in that range. So we don't know if it's 61 or if it's 65 or 62. We don't know, but we know it's somewhere in that range. We're 95% sure it's in that range. One more. So researchers showed that 80% of stray dogs over 2 years of old are in a sample of 500 dogs. So they look at stray dogs. They found, okay, 80% of them were over 2 years old and sampled 500 dogs. Again, to find the margin of error, we do 1 over square root of n, and this time we sampled 500 dogs. That's how many we surveyed. So 1 over square root of 500 is going to be how you find your margin of error. So it's all about the sample size. 1 divided by, oops, I hit the wrong button. Divided by, so I got square root 500. I got 5,000. I did. Okay, 500. And that's how we're going to find our margin of error. So margin of error is 0.045, I guess, if you round it. So this is 0.045, 7 would tell you to round the 4 up. And that would turn into about 4.5%, or yeah, so 4.5%. So 4.5%. So that is 2 spots to get the percent. So the idea is that you're finding this margin of error. Again, it's based on your sample size. The bigger your sample, the smaller your margin is going to be. You see how the previous one, our margin was only 2.8% because we had a big sample of 1,250 people. Now we only have sampled 500, so margin of error is going to get even bigger. We'll see on the project, the second project, that I actually have a limit of requirement. You have to sample at least so many M&Ms for the project, because if your sample size gets too small, your margin of error gets too big. So you want to make sure your sample size is at least a certain account, and that's true to real life too. Your statistician, when they go and do surveys and studies and stuff, they try to make sure they have a big enough sample size so that their margin of error is not too big. Because if you get too big of a margin of error, your data can get kind of useless. If I have to say it's anywhere from 10 to 90%, then that's not very useful. I want to have a smaller range. So big sample size means for smaller margin of error. In this case, we have a bigger margin of error because we got a smaller sample size. It's still not huge. It's only 4.5%. And then we take that and we add subtract it from the study result. The result they got from the study was 80% of stray dogs. So we're going to take 80% and we're going to subtract 4.5%. We're going to take 80% and we're going to add 4.5%. So I get here 75.5%, and here I get 84.5%. So we know the actual percentage of stray dogs, that have are more than 2 years old, is going to be within this range. It's somewhere in there. That's what this is telling us. Yeah, we got 80% from our sample, but our sample is only 500 dogs. There are thousands of stray dogs. So the actual percent that are over 2 years old is going to be in this range. That's the idea. Okay, last thing to do, we're going to talk about hypothesis testing. So hypothesis testing, this whole idea about someone makes a claim. It can be advertisers, schools, lawyers. They're going to make a claim. And we want to test it. We want to say, hey, does their claim make sense? Is it reasonable? Can we believe them? So, for example, an advertiser claims that their product will clear acne in more than 80% of people. So they're saying, hey, our acne product is great. It works in more than 80% of people. To use hypothesis testing, we're going to take a sample of people and have them use the product, and then to determine that sample what percentage it actually works. If the claim is true, if they're claiming that at least more than 80% of people it works them, we'd expect 80% or more people in our sample to have their acne clear up, to have the product work. Now, if the claim is not true, then we'd end up with less than 80%. If we get way more, if we get like 90, 95, then they were hedging their bets. It's not a big deal. But if we get like 60, 55%, then we're going to go, well, hey guys, you said your product works for 80% of people. We're not getting anywhere close to that. And we kind of start to call them liars and say, okay, let's go, look at this. This is where we might file a claim with the Better Business Bureau that you're lying to us about your product. So, 2 possible results when you do a hypothesis. Now, you're going to make what's called a null hypothesis. And that is the fact that, exactly 80% of people have that acne clear up, and the alternative, which is going to be the more than 80%. And the 2 possible results are made into these 2 hypotheses. The null hypothesis, the important thing you need to know about the null hypothesis is always the population value, so the actual real life value, the percentage of people that are cured by this acne treatment, is equal. That's a big thing. It's equal to the claimed value. So they said, hey, it's more than 80%. The null is going to be it's equal to 80%. It is 80%. If I went and did a study and I said, 75% of college students change their majors, then my claim would give me this null hypothesis of the percentage of the change of majors is 75%. Null is always a statement of equality. This matches this. The actual result matches the claimed value. The population value equals the claimed value. The alternative is going to be the other option. It's going to be the value that differs. It's going to be either less than or greater than, depending on the situation. So the alternative is that the population value differs from the claimed value. So up here, null hypothesis was that it clears in exactly 80%, equal to 80%. The alternative is that it clears in more than 80%. They claimed the alternative, and typically our claim will be our alternative. That's typically what will happen. Okay. So you need to be ready to state a null and alternative hypothesis. I'm going to give you some kind of claim, and you have to turn that to a null alternative. So state the null alternative for this situation. You claim that a local gas station is charging more than the national average price of $4. So the null hypothesis for this would be that that this gas station, local gas station, so local gas price, we claim that it's more than $4, but the null is always the statement of equality. So it's going to be the local gas price is equal to $4, the national average price. So null hypothesis is always a statement of equality. We're looking at the claimed value. They claimed it's more than $4 per gallon. $4 was the national average price. So we're going to say that the actual local gas price is equal to $4. And the thing here is, you think about it, gas prices vary from day to day to day to day, and so you can't ever look at all the gas prices, because that would be hundreds of days of gas prices. So we can look at a sample. We can say, I'm going to look at gas prices over 2 weeks. That's 14 days, and I can compare that with the national average. And if it's consistently above, then that kind of would prove me right, and so yeah, it is greater. If it is not consistently above, if it's below a few times, if it's really close to $4 most of the time, then I'd say, I can't really prove it's actually much higher than $4. It's close to $4, the average price. So that's going to be our two options here. So we're going to have this null hypothesis where the local gas price, we're going to say it's equal to, and the alternative, because we're talking about being more than $4, we're going to say the local gas price is greater than $4. I'm not going to really worry about less than, because if it's under $4, well, then it's definitely not greater than $4. So we're not going to really worry about that. Some people include the less than with the equals, because that'd be the other option other than the greater than. For your book and for this test and stuff, we'll always keep those separate, and we'll just do the equals and the other option, which in this case is greater than. If I had said less than $4, then it would have been less than, but I said more than $4, so look at the more than. Next example, scientist claims that 60% of test subjects are able to solve the puzzle without help. She wants to show that more people are able to complete the puzzle. So we want to look and see if we can, prove that it is more people than, the 60%. So our null would still be equals. Doesn't matter what you're claiming, greater than, less than, equal to. The null is always equals. So the percent that solve, the percent of people that can solve this puzzle is equal to 60%, because that was your claimed value. So the actual percent of people who can solve it. So if I go out there and have everybody try and solve this puzzle, we're going to say that percent is equal to 60%. That's what she's claiming. The alternative, since we want to check for more than, would be that the percent who can solve this puzzle is actually greater than 60%. Pick two that are both, more than. Well, that's fairly common, because a lot of times you make claims about it works in more than this or more than that. And you can do less than claims too, but that's the idea. Null is always a statement of equality. The alternative is always a statement of greater than. And then what you do is we perform a study where we take a sample of data, and we compare a result with what the null says. If it's close to the null, then we kind of say, oh, that's close enough. It's not statistically significant. We don't think there's a reason to disagree with the null, and we just let it be. And if it's really far from the null, so if it is much higher than 60% or much higher than $4, then we would say, oh, now we have evidence that kind of reject that null statement and go with the alternative. But you always have to have an null and alternative to a hypothesis test. So the two possible results, after you've set up your hypothesis test, two things that can happen. You always kind of assume the null hypothesis is true. Say, hey, we think it's this is the claim value, it's equal to this. And then we check and say, did the values we get, did they differ a lot from that expectation? So we say, okay, well, if 60% of people could solve this puzzle, then we'd expect, if we did a study, that the answer would be close to 60% of people could solve the puzzle in our study. So what happens is you reject the null if your data doesn't match with it. So you go do your study and you get something way far from that value. You reject the null, and if you have reason to reject the null, it means that your numbers are so far away, you have evidence to support the alternative. So the first option is you might come back and say, hey, you guys claim 60%. I did a study. I got, 85%, and I go with the alternative. In that case, you're helping that doctor out who was doing the study because you wanted to show it was more than 60%. Sometimes you would be helping, sometimes you wouldn't. It depends on what the person's trying to show. But if you reject the null, it's because you have evidence and you're supporting the alternative. Now, sometimes your values, your results are not very good evidence. They're not good enough. So then you fail to reject the null. Now, because we kind of assume the null to start with, we kind of say, hey, we're going to act like the null is true and then check and see if our numbers match up with that. We can't ever accept the null. We can fail to reject the null, which means we didn't show that it was wrong, but we can't actually support or prove the null. So when we fail to reject the null, it means just we lack enough evidence to support the alternative. We never ever prove the null hypothesis. If you tell me that you've proved the null or you've accepted the null is true, you're doing it wrong. So this is, an idea would be going out there and saying, I think that less than 25% of people in the U.S. have good health insurance. And then I go out doing a study, using my definition of what good health insurance is, and I come back and I get 23% of the people in my survey had good health insurance. Well, that is less than 25%, but it's not significantly less, right? 23 is really close to 25. And I just took a sample. I didn't talk to everybody. So the national average could still be 25%. My sample is just, a little on the low side. And so in that case, I'd fail to reject. I'd say, oh, okay, my number wasn't that different from the 25%. I can't really disprove the 25%. So I'm not going to accept the 25%. I'm not going to say it's true. I'm just going to say I failed to disprove it. There's no way to prove the null, because I can't prove that 25% is true, because it could be 23%. My number is just not far enough away to reject the 25%. But if I did that same study and I got 10%, that's way far away from 25%, right? That's a whole 15% off. That would be reason to reject that 25%. So 25% is crap. I was right. It's less than 25%. I support the alternative, result. Those are the two options. You can reject that equality statement and support the alternative if you get good enough evidence, if your number is really far away from the equals, or you can fail. If your number is too close to the equals, even if it is lower or higher like you expected, if it's too close to the equals, you fail to reject that equals. You don't prove it, you just fail to reject it. That's why it's called failing, because when you fail, it's because you don't have enough evidence to prove anything. You can't prove something this way or that way. You just weren't able to prove it. That's what we're doing. So we're going to do the null and alternative hypothesis for these ones, and then we're going to talk about the two possible outcomes that can happen. So for example, you claim that more than 90% of college students graduate with student loans. The null, in this case, would be that the percent, with loans, so the percent of students that graduate with loans is equal to 90%. Because null is always a statement of equality. Yes, it is a more than claim, but null is always a statement of equality. The alternative is going to be either differs. So your alternative is going to be the percent with loans is greater than 90%. Again, null is always equals. Alternative is always going to be the other option, the greater than or less than. In this case, we're talking about more than 90%, so it's going to be the greater than. Now, there's two options. Option one is you reject the null, which tells us we support the alternative, because if you reject the null, that means you go with the alternative. And that would tell us that more than 90% have loans. This is what would happen if you went and did your study and instead of getting like 90%, you got like 95 or 99%. You got way higher than 90%. Your values were significantly above 90%. And then you'd say, hey, look, it is greater than 90%. That's what I got from my sample. Even though it's just one sample, it's high. It's so much higher than 90% that we can say, yeah, yep, we don't believe 90%. We think it's actually above that. It is greater. In this case, you have proved the claim. Option 2 is to fail to reject. And if you fail to reject, it means we can't support the alternative. It doesn't mean that you've proved the null. It just means you can't support the alternative. We don't have enough evidence to prove anything. You fail when you don't have enough to prove something. If you fail that we can't prove anything. So we're not going to say we support, we have 90%. We're not going to say there are 90% with loans. We can't prove that. Our data doesn't disagree with that, but we can't prove it. We can't. That's not how these studies work. You can't prove it. It's kind of like science class. You learn how you can test a theory, but you can't prove a theory. It's kind of the same thing here. You can test a null, but you can't prove a null. You can test it, and if you find it lacking, toss it out and go with the alternative. But if you can't reject the null, then you just have to let it fly. You can't mess with it. You can't prove it. This would be what happens if you got like 91%. Yeah, it's still more than 90%, but it's not that much more. It's not significant enough. You need something high enough, bigger than 90% enough that you can reject that 90%. So in this case, we would say, I got 91%. That's too close to the 90%, so I didn't get to reject the null. I just have to let it be. Okay. One more. A claim that the mean wait time at a grocery store is less than 4.5 minutes. So they're saying their mean wait time is less than 4.5 minutes. The null statement would be that the mean wait time, so the average wait, is equal to 4.5 minutes. And the alternative would be that the mean wait time is less than 4.5 minutes. Finally, I did one with less than. It works both ways, right? You can do greater thans or less ones. With this one, you definitely want a less than because we're talking about less than 4.5 minutes. The grocery store is trying to say, yeah, people don't wait that long. It's less than 4.5 minutes. First option, if you reject, so you reject the null, this is where you actually have enough evidence to show it is actually less. You actually support the alternative, and you've shown that the wait times are less than 4.5 minutes. So this is where you go do your study. You go wait in line at different times, different days over like a couple weeks, and you record your wait time each time, and you get an average of like 2 minutes. And you say, 2 minutes is way less than 4.5 minutes. I have real good reason to believe that they're right. It is less than 4.5 minutes. I'm going to support this alternative. I'm going to support their claim and say, yep, it's less than 4.5 minutes. The other option is to fail to reject. And this means we can't support the alternative. We do not have good evidence to disprove the alternative, the null hypothesis. So this is where you go in and you do your survey and you find out, okay, my average wait time was like 4.3 minutes. And yes, that's less than 4.5 minutes, but it's not significantly less. It's not a big deal. There's not enough of a difference. So we'd say, I can't disprove their 4.5 because even if the average wait time is 4.5 minutes, 4.3, I could get that just from my sample because, again, I'm not doing all the wait times. I'm just doing a sample of them. And my number is going to have a little variation. So anything that's close but not that big a difference, not a big deal. So for hypothesis testing, you know how to state the null and alternative. You need to talk about what happens when you reject. You reject the null, and you support the alternative. And when you fail to reject the null, and you can't support the alternative. Again, it's always about rejecting the null and failing rejecting the null. So we're looking at the equal statement and saying, does our data match up with the equality? If it does, we'll leave the null and say we can't reject it. You don't ever say you accept the null. You say I failed to reject the null. Or if we have evidence that doesn't line up, then we reject the null and we support the alternative. Okay, now just like before, it'd be nice to quantify this because I just keep saying close, far, which doesn't really mean a whole lot. The way they do this, the way we kind of quantify this is going back to that 1 in 20, that 5% test or the 1% test. So we use statistical significance to decide whether to reject or fail to reject the null. We compare the statistic, the value we got from our sample data, with the claimed parameter, what someone says they think about is true about the population, and then look at the probability of getting our statistic. The lower the probability, then the more likely we are to reject the null. That gives us evidence to reject the null. So we look at the chance of getting our sample result, and if it's more than 1 in 20, so if it's large, if it's more than 1 in 20, so you have like a 10% chance of getting this, or 20% chance of getting this, anything bigger than 5%, then it's not significant, and it does not give sufficient evidence to reject the null. So this is when you say, I failed to reject. You fail. So anytime your probability is too high, we call this the p-value, the probability value. When your p-value or your probability value is too high, the likelihood of getting the result is too high. It's so close to the actual value that you can say, hey, we could just get that by chance. It's very likely to happen. Then we fail to reject. Now, if your probability is less than 1 in 20, so less than 5%, not more than, but less than, then it's significant and you have moderate evidence to reject the null. It's not the strongest evidence ever, but it is evidence to reject the null. In this case, you probably would reject, depending on your testing parameters. Some people might have stricter parameters and say, well, I can't reject at 5%, I'll have to go all the way down to 1% level. But most of the time, if you're just doing a casual study, you'd say, hey, 5%, it's less than 5%, but that's enough for me to reject the null and support my alternative. If you really need to be strict, you can go down to the less than 1 in 100, less than 1% chance. And then you're significant at the 1% level, and you have strong evidence for rejecting the null. So basically, everybody would reject at this point. Like, there's no one that would say, oh yeah, I'm going to still fail to reject. No, at this point, you're definitely rejecting, because no matter how strict you're trying to be, this is evidence to reject. So the likelihood is going to be determining what happens. I'm not going to be so worried. I'm not going to test yet which level and stuff on the null, because I'm really not more worried. Can you state the null hypothesis, the alternative hypothesis, and the result of those? That's really what I'm going to focus on. I'm not going to worry about quantifying it too much, because we're not going to be actually performing in real life a lot of these studies. But it's good to know how they work, so that when you see someone do a study and test someone's claim, you know what they're talking about. And that's what we're learning here. Okay, last example though. This is how you would do it. So say a nurse at a hospital believes the male baby weights have been usually high this year. She believes the weights have been higher than the national average of 7 pounds. So she's looking and comparing that with the national average of 7 pounds. A random sample of 150 babies born at the hospital has an average of 9.5 pounds. And that is higher than 7 pounds. But we have to look at the probability of that happening, because there's some natural variation. Remember, just because you're above the average doesn't mean that's guaranteed rejection kind of thing. So assuming that the mean birth weight of the hospital is above the national average 7 pounds, calculations show that the probability of selecting a sample with 9.5 pounds is 0.034. So this is your probability, and this is what you use. You look at the probability, the likelihood of getting that sample result, and that's how we test our null and alternative. So we're going to formulate our null and alternative, and then we're going to discuss what this sample result tells us. Okay, so first off, what are the sample result and its probability? So our null is that the birth weight average for this hospital, so the birth weight average is equal to the 7 pounds. Yeah, we know it's not from our sample, but we're talking about all the births at this hospital. 150 is a lot of births, but they're probably doing hundreds and hundreds per year. So this is just, we're saying the actual birth weight average for this hospital is equal to 7 pounds is our null statement. Our alternative is that the birth weight average is greater than she claimed, right? She said that she thinks it's unusually high. She believes that it's higher than the national average of 7 pounds. So she thinks it's greater than 7 pounds. Now, her result, the result of 9.5 pounds is higher, but if it's not high enough, it wouldn't be significant enough to reject the null. So what we have to look at is it has a probability of 0.034, or 3.4%. So that percentage is not less than 1%. So it's not the dead giveaway like always reject, but it is less than the 5%. So that is less than 5%, which means that we have moderate evidence for rejecting the null. So we would reject in this case, unless she has some reason why she wants to use a really strict, okay, you have to be below 1% to reject. This would be moderate rejecting evidence. So we would reject, and we would say, yep, it's been pretty high. It's been significantly higher than reject the equal 7 pounds, and we would support the greater than 7 pounds. And it's all based on this probability. So I'm not worried about making you figure out what the probabilities are in my actual statistic class. That's actually part of the job they have to do, is they have to figure out, okay, if I'm doing a hypothesis test, I need to figure out what the probability of this result is. I look at that 9.5 pounds and say, what are the chances I got 9.5 pounds when I thought it was going to be about 7 pounds, because that's our null. And they find that probability, and then they use that probability to determine whether or not to reject. And we just get given the probability. We say, oh, it's 0.034, so 3.4%. And we say, oh, that's low enough, we can reject. As long as we're not trying to be super strict and saying, reject up to like the 1% level. If you're rejecting at the 5% level, that's fine. 3.4% is below that, that's good enough. Okay, so that's it. We are done with statistics. This is our last section for statistics. So you should be getting ready for that test. As always, I'll have the practice exam posted up into my lab in D2L. If you need help getting ready for that exam, please let me know. Have a good one, and see you on the next time.